Greetings and welcome to Chapter 3 in Calculus 1. We're going to be starting with Section 1 in Chapter 3, and as I talk about the content in this video, I'm going to be using some notes that were adapted from material from Calculus with Applications by Greenwell et al., and many thanks to the publisher Pearson. And in this section, we're going to be talking about, if I can get my cursor in the right spot, we're going to talk about limits. And limits are a key component to the conversation about calculus. And the first thing that we see in this section is this notation down here, like almost in the middle of your screen. And we're going to talk about the details of that. And what's really happening when we talk about the limit of a function is we're going to be looking at a function. We'll look at some specific functions, and we're going to take x values, and in a way we're going to be plugging them into the function. And in fact, we're going to do exactly this. We'll plug in some x values that get closer and closer to a particular value. And what you're seeing, if I can zoom in here, I know it gets a little pixelated. What this says, what I've circled here, if we read this, it says the limit of f of x as our x values approach a, and a is going to be a specific number, equals L. So again, our x values are going to be approaching a specific value. And this L that's on the right-hand side, if the limit does in fact exist, that L value is going to be a y value. And the question is, as our x values get really close to this value of a, what does it seem that our y values are approaching? And I can't stress enough, and I'll mention it as we go along, I don't actually care what's happening when x equals a. I just want to know what's happening, or what do our y values look like when we're very, very close to it having an x value of a. So you're welcome to read through any and all of this material, and it will say pretty much what I've just said, just in slightly different words. And because it's math, we have to make this statement and say that the idea of getting closer and closer to something isn't a formal definition. The second bullet says that this is a key concept. The third bullet says that calculus was discovered by Isaac Newton and the German mathematician Gottfried Leibniz. Leibniz is also one of my favorite philosophers. We're going to be, in the next bullet it says, finding limits in 3 different ways. We'll look at them graphically and using tables, and we'll do some algebraic manipulations. And I just mentioned this, but it's worth mentioning one more time, is that the limit is a value of y, not x. We're going to be moving our x values closer and closer to a specific x value, as I said, but then ultimately we want to know what's happening with the y values of that function. As far as notation is concerned, and this will be important, this statement says the limit of f of x as x approaches a from the left, and the next one as our x values approach a from the positive side, or from the right. And this one is effectively talking about, or looking at, or finding the limit as x approaches that a value from both sides. And we'll discover that it's not always the case that as our x values approach a from the left and from the right, that the y values are doing the same thing, or approaching the same y value. So we'll discover that with some specific examples. Here's a great example, and we'll talk about it in greater detail than the question actually calls for, but Notice that the question is asking us to decide whether the limit of f of x as x approaches 1 from the right, if it even exists. And if it does, find the value. So what we do is, obviously you can see our x value of 1 down here. And I'm going to put my pen on my function, and I'm approaching a point that has an x-coordinate that's closer and closer to positive 1, and I'm coming in at it from the right, obviously. And as I come in from the right, what are my y values doing? They're increasing, and they're getting closer and closer to a y value of 3. Now, when x actually equals 1, you can see that there's a hole there, at least on the lower part of this graph. And just to the right of that hole, or that jump discontinuity, my y values would probably be 2.9999999. They're approaching a y value of 3. And that's all I'm concerned with. Again, when I'm looking at a limit, I'm not actually concerned with what's happening when x equals positive 1 in this case. I'm only concerned with what my y values are doing as I approach the number 1. And so again, as I approach from the right, my y values are approaching positive 3. So your answer would be positive 3. Let's examine this as we come at it from the right. Or sorry, from the left. Our y values are getting larger, getting larger, getting larger. Our y values are approaching a y value of 4. And again, I don't care that they actually do achieve a y value of 4 as I'm coming in from the left, because I'm never actually going to arrive at an x value of 1. In this case, in blue, I'm staying just to the left of, or just less than, an x value of 1. And my y values look like they're approaching 4. So interesting that we could look at a function and the limit approaching from the right here does not equal the limit approaching from the left. 3 does not equal 4. We'll find out and see again in a later problem that if the limit from the left does not equal the limit from the right, then we will say generally that the limit as x approaches 1 does not exist. We have to have consistency. The limit from the left needs to equal the limit from the right. Here, decide whether the limit as x approaches 0 for f of x, does it actually exist? In this case, it does, because the limit as we come in from the left has our y values trending towards 0. As we come in from the right, again, our y values are getting smaller, smaller, smaller. Our y values are definitely trending towards 0. And so we can safely say that the answer to this question is 0. Let's write it up formally. The limit of f of x as x approaches 0 from the left equals 0. Remember that this is a y value. Also, the limit of f of x as x approaches 0 from the right equals 0. And since 0 equals 0, we can say that the limit as x approaches 0, and because I didn't put a little plus or minus on this, I'm saying from both sides, as the limit of f of x as x approaches 0 from both sides equals 0. So this would be your final answer to this question. The limit does exist, and it is 0. The answer to this question would be DNE, does not exist. This problem asks us to evaluate the limit as x approaches 1 for the given function using a table method. And so I've already filled this in for us. Coming at it from the left, you can see that my x values are starting at 0.9 and then 0.99 and then 0.999. They're getting closer and closer to an x value of 1, but from the left. Coming at it from the right, x values starting all the way to the right at 1.1, and then we lower our x values. We move in toward that x value of positive 1, getting closer and closer to 1. And if you look at what's happening as we come in from the left, look at what's happening to these y values. They look like they're getting closer and closer to 4. And as we come in from the right, I've got 4.6, 4.06, 4.006. Looks like as we're coming in from the right, our y values, our f of x values are also approaching 4. Since the limit from, so let's say it as thoroughly as possible. Since the limit of f of x as x approaches 1 from the left equals the limit of f of x as x approaches 1 from the right, and since they both, so they're equal to each other from the left and from the right, and they both equal 4, we can say that the limit of f of x as x approaches 1 is equal to a y value of 4. There's a nice way, if you have a graphing calculator, to get these x values instead of having to type it in with all the decimals and raising it to the 4th power over and over again. What I did is, in my graphing calculator, I've got a TI graphing calculator, TI-84. I hit the y equals button, and I'm going to fight the glare a little bit. I went into y equals, and using parentheses, I typed in this equation. And then I hit the second button and the table button. Oh, sorry. Quit out of there. Second mode for second quit. I hit the second button, and then I hit table set, which is above the window button. And second window, so it takes me to this table set menu, and I started my table value at 0, and then delta table is describing the distance that it's going to march through some x values. If you then hit second and the graph button, which is table, it puts you into table mode. It's actually showing us in the left-hand column a list of x values starting at 0 and increasing by 1/3. So it goes to 0.33, 0.66, and then 1. And then it shows the corresponding y values. Well, that's nice, except that this table that we're looking at in this problem isn't increasing by this consistent amount of 1/3. So what I then did is I hit my second button again on my calculator, and the trace button above it, it says Calc. So I did second Calc, and my first menu option is value. So I hit enter on the calculator, and mine has already been drawn, but if yours hasn't graphed it yet, can we get it? It's a little rough. It's going to draw a graph of this function, at least part of it. And at the bottom of the screen, you can see a blinking cursor. It's probably not focusing, but you can see it blinking down there. It says x equals. And what I did is I typed in 0.9, or just 0.9. 0.9, enter. And it puts my cursor on the graph at the point where x equals 0.9. And at the bottom of the screen, it shows me the corresponding y value, which in this case was 3.439. And so that's what I wrote down as my first entry on my table. Then, in order to type in a new x value and get out a new y value, I did second Calc. First menu option is value. I hit enter. and that restarts the process and gives me my x equals with the blinking cursor, and I was able to type in 0.99, enter, and it gives me the corresponding y value. So that's a nice way to not have to type in this formula over and over again. There's another way to do it where you can store your x values. I don't remember how to kick out the y values, however. Can I do alpha y? Where is it? That works. Another way that you can do this is after you have that equation typed into y equals mode, you can come into your home screen where you've got nothing. You would do 2 plus 2, enter, right? Something like that here in the home screen. I'm going to type in 0.9, and then down here in the almost the bottom left corner of my calculator, above the on button, the second button up, it says STO with an arrow. If you hit that button, it puts a little arrow on the screen, and then you could just hit your regular X button as though you were typing in an equation in y equals mode. It has an X and a T and a theta and an N. So I hit X. So now it says 0.9 and the arrow and the X. And what that means is it's going to store the number 0.9 in the variable X. And I hit enter. Now I'm going to use this green button that says alpha. So I'll hit that. And then on your keypad, find the letter Y. So my alpha button was green. The letter Y is green. It's above the number 1. So now I've got the letter Y on my screen, and I'm going to hit enter. And it says, excuse me, 3.94, which unfortunately is the Y value that corresponds to an X value of 0.99. Okay, so forget that process. I obviously have to refine that a little bit and figure out how to get it to process the designated X value through that Y1. But the first process works of using the table set and then second calc. I wish I could remember how to do that. Okay, anyway, I filled in this table for us, and we can see that those values are coming in closer and they're approaching the y value of 4. But the way that I got those y values on the bottom part of the table was by using that particular feature of my graphing calculator. Now let's come in and look at some of the rules, not all of them, but let's look at a few of the rules for limits. And the conversation about these rules is based on these first two sort of definitions that say that the limit as x approaches a is equal to a, and the limit of g, this other function, as x approaches a is equal to b. So we've got two different functions, but our x value is approaching the same number, a. Number 1 says that if k is a constant, then the limit of k as x approaches a is k. That's not a big stretch. And we're going to see some of these in motion. So reading through stuff like this in generality doesn't necessarily give you a lot of insight, but just be aware that there's a rule if your limit is being applied to a constant value. Number 2, you can see in the square brackets there that we have f of x either being added or subtracted to the g function, and then the limit is being applied to that sum. And to the right of the equal sign, what it looks like is that you can distribute the limit over addition, applying the limit individually to those two functions, finding or evaluating those limits, which gives you the a and the b, and then whatever those two numbers are, you can add them together as long as the limits exist, which here they do. They've been defined as equaling some specific values, capital A and capital B. Number 3 gives us a similar property, except this time it's multiplication, so you can, so to speak, distribute your limit over a product, and then you see the a times b at the end there. The limit of a product is the product of the limits. I like that. Multiplication and division are so similar that we shouldn't be surprised that number 4 says that you can distribute to the numerator and the denominator as long as the limit in your denominator doesn't end up going to 0. Then you would have division by 0. If you're working with a polynomial in number 5, something like x squared plus 3x plus 9, or even 7x to the 12th power minus pi x to the 2nd power minus a quarter, if you're applying it to a polynomial, all you have to do is take that a value and plug it in. The polynomial, the graph of the polynomial, it's a continuous function. You don't have any asymptotes, any holes, any jumps, so you can just go and do direct substitution and find your limit. It's nice when that happens. For any real number, we can see that we have an exponent in number 6, and this one's a little subtle, but here you can see that the limit is on the outside of our square brackets, where our function is being raised to the power of k, and after this equal sign, you see that we could evaluate the limit of our function as x approaches a first, get an answer, and then apply the exponent. So in this case, the limit of f of x as x approaches a is equal to capital A, so we take the capital A, raise it to the power of k, and you got your limit. Again, of course, provided that the limit exists. If two limits are equal to each other, if the functions are equal to each other, that makes sense. And number 8 and number 9 are very specific. We're getting into exponential functions and the inverse of those, which would be logarithmic functions. I don't want to spend too much time on those. We'll deal with them if and when we run into them. And then we have our first example, example number 3. Undoubtedly, we're going to see some examples now where we get to use those properties. And the numerator of this rational expression is a polynomial, x squared minus 81. And the denominator is x minus 9, which is another polynomial. I wonder, could we just do direct substitution and plug in our a value of 9 in place of x? Could we plug in a 9? Oh, that was supposed to be a highlighter. Could we plug in a 9 for our x value in the numerator? Sure, 9 squared is 81, 81 minus 81 is 0. 0 in the numerator, no problem. 9 minus 9 in the denominator gives us 0. That's a problem. So what in the world am I supposed to do in this situation? Maybe it's jumping out at you, but remember that x squared minus 81 is a difference of squares, which is factorable. So I'm going to rewrite this as the limit as x approaches 9 of x plus 9 times x minus 9 all over x minus 9. The x minus 9s are going to cancel, and we can rewrite this statement again as the limit as x approaches 9 of this function x plus 9. We no longer have a rational expression. We no longer have a variable in the denominator. X plus 9 is a polynomial, which means that we can evaluate this limit by direct substitution, taking the value of 9, plugging it in for x. This is equal to 9 plus 9 equals 18. Don't just copy down what I've written. You need to insert some sort of articulation about the fact that maybe you want to note that this was a factored difference of squares. Certainly canceling this out, that's not a big stretch for you. But in order to go from here to here, we did that because x plus 9 is a polynomial, which relates us back to, which rule or property was that? It's number 5. So you might put a little note right here that says polynomial see property number 5 on the previous page, or words to that effect. And then we have this expression. Definitely as h approaches 0, we have a problem in the denominator. What you might recognize is that this expression that we're evaluating is the difference quotient. And it's the difference quotient being evaluated for the function x cubed. And what you might also remember is that when you evaluate the difference quotient for a function, the terms that are part of the original function should cancel out, all of them, if you take the time to expand or FOIL and combine like terms. So I'm going to expand or multiply out this numerator, well, in a way, because do you remember Pascal's triangle? It looked like this: 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. This is Pascal's triangle. You probably learned about this as part of a lesson on the binomial expansion theorem, and you also learned about n choose r, which you already knew from a stats class, but then all of a sudden you were applying it in yet another math class. Ooh, too far. Take me back. Where'd it go? Okay, so I'm going to use that as a little bit of a cheat in order to expand this polynomial. So I know that this is going to equal the limit as h approaches 0 of x to the third plus, that's the 1, plus 3 x squared h to the first plus 3 x to the first h squared plus h to the third minus x to the third. And this x to the third is this x to the third, and it's all divided by h. And then I'm going to combine like terms. As I said, this one is going to cancel out with this x to the third. So let's rewrite this again. H is going to 0, and our fraction now says 3x squared h plus 3x h squared plus h to the third. Those x cubed terms disappeared. We do still have the denominator of h, and fortunate for us, every term in the numerator contains a factor of h. So we can distribute our division. All right. No more denominator. I'm thrilled. Maybe you want to put square brackets around this or something. That way the limit doesn't only get applied to the first term. That's probably technically the best move and the best notation there. We didn't have to worry about it up here because the division that's happening here kept that all kind of bundled together. But once we have it just as separate terms, probably a good idea to put brackets around it. And now this looks to me like a polynomial. And we can perform direct substitution. Let's plug in the h value of 0. And you get a final answer of 3x squared. I happen to know that the original function was x to the third, and I also know that the process of taking the limit and sending h equal to 0 and applying that limit to the difference quotient is a This is sort of the long version of a process that we're going to learn about later in this semester. Not too far, but we're going to learn a shortcut that will allow us to literally skip pretty much everything that we just did here. So I'm looking forward to showing you that, but this is what's really happening behind the scenes. This idea of numbers getting exceptionally close to other values, and that idea of infinity and being infinitely close to something, that is a really key concept that's part of the study of calculus. The existence of limits. The limit of f as x approaches a may not exist. And we actually already had this conversation, so you could read through what's in this sort of brown colored box. And it talks about the fact that the limit in number 3 specifically, how the limit from the left has to equal L and the limit from the right has to equal M, and that if those two limits don't equal to each other, then we say that the limit does not exist. So we talked about that earlier in this section already. The other thing that's being addressed here using words, and it's much more easily seen using pictures, and we're going to see one on the next page, is that in number 1, almost in the middle of your screen, if as your limit of f of x as x approaches a, if your y values get exceptionally large, if it looks like they're heading off toward infinity, or if they get really large in the negative direction, then we say that the limit does not exist. While that's true, there are going to be times where it would be a good idea to realize that maybe the limit as you're coming in from one side is going up toward positive infinity, and the limit as you're coming in from the other side goes toward negative infinity. It might be beneficial to note that. Ultimately, will the limit still be denoted as not existing? Yes. However, good idea to have your eye on the big picture before you draw a conclusion. And number 2 talks about exactly what I just illustrated very technically with my hands. And thankfully here is a proper illustration, so I don't have to bring my hands into the frame again. The left-hand side of this is a proper diagram of what I was just trying to illustrate. So as we're coming in from the left, we're going up toward positive infinity. As we approach an x value of -6 from the right, it's going down toward negative infinity. So we would say that the limit as x approaches -6 does not exist. What about here at -4? As our limit approaches -4, or as our x value approaches -4 from the left, it looks like we're approaching a y value of 2. Might be a little bit tough to read. As our x value approaches -4 from the right, it looks like we're approaching a y value of 3. And since 2 does not equal 3, we would say in this case yet again that the limit, again, hard to read, that the limit of f of x as x approaches -4, we would say that that does, little dyslexia there, that was fun, that the limit does not exist. Okay, the limit of f of x as x approaches -4, and that means from both sides, it doesn't exist, because as it comes in from one side, it equals a different value than as it comes in from the other side. Now, what about as our x values approach 0? So now I'm operating in here. I'm just going to switch up my color a little bit here. As my limit comes in from the left, we're approaching a y value of what looks to be about 3.5. As the x values come in from the right, it also looks like our y values are approaching 3.5, and so we can say that the limit of f of x as x approaches 0 equals, I've been saying 3.5, now I can see up here that this says 3.4. We were close. Another scenario, instead of one side approaching toward positive infinity and the other one toward negative infinity, here, as we're approaching an x value of 3, both of these curves from the left and from the right are diving down toward negative infinity. And it could be said, and it is written here even though it's really fuzzy, this says that the limit of f of x as x approaches 3 equals negative infinity. And then it goes on to say, so the limit does not exist. Even though they're both approaching negative infinity, is it possible you could run into a scenario where a correct response would be negative infinity? I suppose so. Negative infinity isn't really a real number, so that's why we might say it does not exist. And this is the one that we hope and pray for. Our curve is continuous, there are no holes, there are no asymptotes. As x approaches 6, your y value is 2. This illustration over here is a smooth, continuous curve reminiscent of a polynomial. And so we were able to go with direct substitution and just go in there and grab the y value that's associated with an x value of 6 and present that as our limit. We love when that happens. It makes our lives so much easier. All of the limits we've been talking about so far have been taking our x value and having it approach some specific value. What about limits at infinity? What if what we're interested in is what happens to our y values as our x values get extremely large, whether it's really large in the positive or negative direction, positive or negative infinity. That is something that we may have to contend with. And there are a couple of additional little properties that we are going to look at. And the first one says, for any positive real number n, and this exponent down here says n, if our x value is approaching positive infinity, then the limit of this expression equals 0. Because you're taking 1, and when x gets really big, you're dividing 1 by an extraordinarily large number. And to go from a tenth to a hundredth to a thousandth to a billionth, you can see that just using those kinds of numbers, as your denominator grows, the value of your expression gets smaller, and it gets closer and closer to 0. That would constitute, or graphically, it would look like you have an asymptote that you're approaching. So you're never actually going to reach a y value of 0, but that's what it's trending toward. And the very same conversation can be had about this expression, except this time we're taking x and sending it really far to the left toward negative infinity. So those end up equaling 0. And finding limits at infinity where our function f of x is equal to a polynomial p divided by a polynomial q, where q does not equal 0, and both limits at infinity can be found. So as long as all of those things are satisfied, then we can have this conversation that says that in order to evaluate the limit of f of x as x approaches positive or negative infinity, what you should do is divide p and q by the highest power of x in q, which is the denominator. And then you should use the rules that we were just talking about, where I have these red circles at the top of the screen. And thankfully, immediately we have the opportunity to put that into practice. So here, we're evaluating a limit as x approaches infinity for an expression that has a polynomial in the numerator and the denominator. And in order to solve this, I'm going to multiply the numerator and denominator by 1 over x squared. Why am I allowed to do that? What's that equal? Anything divided by itself is equal to 1. So what I'm really multiplying by is 1. Multiplication by 1 doesn't change the value of anything, but it does change what it looks like. And so let's use this version of the number 1 in order to, I was going to say simplify our original expression, but it doesn't actually get a whole lot more simple looking. Let me switch colors so that we can tell the difference between one and the next. So we still have the limit as x is approaching infinity, and in the numerator we end up with, let's make a numerator. We end up with 5 plus 6 over x minus 3 over x squared. I've distributed multiplication by 1 over x squared and simplified, and this is what we get. In the denominator, we end up with negative 4 plus 5 over x squared. And maybe let's put brackets around it. We're applying the limit to the whole thing. Let's refresh our memory on some of these rules. The numerator and denominator are no longer polynomials, but we are taking the limit and applying it to a fraction or to a rational expression. Let's see what the rules are. I don't know if I want to use that rule just yet. I'm going all the way back to the long list of rules. Yes, this is what I wanted. I'm applying the limit to a quotient. And this says that the limit of a quotient is the quotient of the limits. So we're going to sort of distribute the limit into the numerator and the denominator. Another feature that I'm going to use, another property of the limits that I'm going to use, is number 2. The limit applied to a sum or difference, you can sort of distribute the limit to all of the terms in that expression. Now in purple here, we have our fraction. I'm going to apply the limit to the numerator and to the denominator. Let's write it out. The limit as x approaches infinity of 5 plus I'm gonna switch this up a little bit. Should I do that? Yeah, I'm gonna write this as 6 times 1 over x minus 3 times 1 over x squared. All divided by. Now I'm applying the limit to the denominator. X is still going to infinity. We're applying that to negative 4 plus, be careful, I'm going to write this as 5 times 1 over x squared. All right, and then I'm going to use that second property that we saw that says I can take the limit and distribute it to all 3 terms in the numerator. I can take the limit and distribute it to both of these terms in the denominator. And I apologize, I'm going to go scrolling up again. I want to show you one more property that's going to come into play here. I can't anticipate everything. The other property I wanted to highlight for you was number 1. This first property allows me to, this is the part that I'm most concerned with, and this part in here make that a little bigger. So here I have a constant value being multiplied by an expression, and on the other side of this equal sign, the constant value has been factored to the outside of the limit. It appears now to the left of the limit instead of being inside of those square brackets, and we're only applying the limit to the function. So I'm going to use that property also. That's property number 1. And really the first part of property number 1 said that if you take a limit and you apply it to a constant, the result is just the constant. So we're applying number 1, and I think it was number 2 that allowed us to distribute the limit. Let's just see. I'm going to switch colors again to red. So we'll switch colors from line to line. Now I've got the limit as x approaches infinity of 5 plus 6 times the limit as x approaches infinity. You're going to get really tired of writing the limit as x approaches infinity of 1 over x minus 3 times the limit applied to 1 over x squared, all divided by we're applying the limit now to this constant value of -4 plus 5 times the limit applied to 1 over x squared. Are you having fun yet? You have to find a way to make this process as zen as possible. The fact that we have the opportunity to sit around, probably in an air-conditioned environment, or you're watching this video on a computer, you're enrolled in a university, and you have the time and the ability and the financial wherewithal to sit around learning mathematics. Life is good. Life could be a lot worse. A lot of people would kill for the opportunity to study stuff like this. So, while you feel like you're really sweating it out, grinding through these problems, don't forget just how fortunate you are. The properties that we talked about 3 or 4 slides up said that the limit being applied to a constant value like 5 equals just that constant value plus 6 times, and now we're applying the limit as x goes to infinity to 1 over x. And just up here on the previous page, we said that if we're applying the limit as x goes to infinity to 1 over x to some power, the result is 0 because the denominator gets crazy big. It doesn't matter whether it's x to the first power or x to the second power. Here we've got x to the first power. Here we have x to the second power. Both of those are going to turn into zeros. So is this one. So let's write this in, turning it into zeros. We've got 6 times 0 minus 3 times 0, all divided by the limit here being applied to a constant value is the constant value, -4, plus 5 times yet another 0. And so our final answer, after we clean it up, is -5/4. You know this already, I suppose, but I'll mention it that the negative was originally in the denominator with the 4. I could have moved it up to be with the 5 in the numerator, or I can place it next to that division bar, that fraction bar. Negative 5/4. Couldn't I have just gone in here and realized that this was my answer? Sure, I did. I knew what the answer to this question was in like 2 seconds. Why do I have to write all of this out? Because this is a demonstration of understanding. This is a practice of utilizing properties that might have to be used to solve a different problem where you can't simply go in and circle the leading coefficients. Like this problem, you can't simply go in and circle the leading coefficients. Why not? Because in the numerator you have an x, and in the denominator you have an x squared. They don't have the same power. They're not of the same degree. Were they in this problem? Oh, they were. They were both x squared. And when we divided by x squared on the top and the bottom, both of those x squareds disappeared and left us with constant values, which when you apply the limit to a constant value, nothing happens. You're left with the constant value still. And the denominator under this became an x, and under this became an x squared, and under this became an x squared, which is why all of those turned into zeros, and these x squareds canceled out, leaving us with negative 5/4. That, however, is not the same scenario as we're looking at here. What is it that we're supposed to divide by in order to solve this problem? You're supposed to divide the numerator and denominator by x to the largest power in the denominator. So we're going to divide top and bottom by x squared and then apply the limit. Sometimes my pen works, sometimes it doesn't. So let's shorten the process a little bit. Let's do some arithmetic in our head. We're going to divide all of this stuff up here by x squared, and we're going to divide all this stuff down here by x squared, and let's just write down the result. In the numerator, we're going to get 5 over x plus 1 over x squared. In the denominator, we'll get 11 minus 7 over x squared. We now know that we're going to apply the limit to this, and to this, and to this, and to this. We also know that the limit being applied to this term, because there's an x to the first power in the denominator, and we're sending x to infinity, that's going to turn into a 0. And here we've got x to a power in the denominator, so that'll turn into a 0, and ditto for this one. So after we apply the limit, we end up with 0 plus 0 over 11 minus 0, which equals 0 over 11, which equals 0. Now, if you have an instructor who requests that you solve this problem by applying the properties of limits and that you must show your work, your answer to this problem better look a lot more like your answer to the previous problem. They might even want you to number or put in some kind of annotations about which property you used. You may want to go back through this video, having already taken notes on this, and listen as I was reminding you which one of those properties we were using, or just take your notes and scroll back up or rewind in the video so that you can see that list of properties and try to identify the properties on your own. That would be the best way to learn and help remember which properties were used when. In this problem, again, we're dividing by the largest x value in the denominator. We can do this one as fast as we did the previous one, and it's worth doing because the result is a little bit different. This is equal to the limit as x approaches infinity. And sorry, we're going to divide the numerator by x squared. We'll divide the denominator by x squared. And in the numerator, we get 6x to the third minus 1 over x plus 4 over x squared, all divided by 9 minus 1 over x minus 6 over x squared. And when we apply the limit, this term goes to 0, this term goes to 0, as does this one and this one. We know that from the previous couple of problems that we worked on. X is in the denominator, and you send x to infinity, the denominator becomes really big, which makes the value of each one of those terms equal to 0. What about these other two terms? Well, this one, that's going to stay 9, because when you apply a limit to a constant value, nothing happens. But what about this last one? What happens when we take and apply the limit to this? It's not difficult to imagine. You're going to take an obscenely large number as it rattles off toward infinity, and you're going to cube that number. And then you're going to multiply it by 6. You're going to take really big and turn it into really, really, really big, and then you're going to multiply that by 6. I'm trying to remember in that table, or that list of properties up above, if there was a specific property that addressed what happens, or how to be able to declare for sure that a term like this one is going to go off to infinity. You should go up and check that out. And you should also be aware that infinity divided by 9 is still infinity. Therefore, this limit does not exist. The 3 dots in a triangular pattern like that mean therefore. The last page of these 3.1 notes give us an application problem or a word problem. This one says that the cost of manufacturing a particular watch, and that's, is C of x, and it equals 9,000 plus 9x. So x represents the number of watches produced. So this cost function that we see right here is really representing the cost of manufacturing x particular watches. Okay, that's a better description of what that function is. The average cost per watch can certainly be found by knowing the cost to produce all of the watches and then dividing by the number of watches. That's how you find an average, right? Add them all up and divide by the number of numbers. Well, this function right here, C of x, that's adding up all of our watches. That's the total cost of producing that many watches. To find the average, we'll take that cost function, and over here in the bottom left, we're going to divide it by x. And then the question is to find the limit as x approaches 1,000 of the average cost of a watch. So if we were to produce 1,000 watches, what would be the average cost of producing those 1,000 watches? What would be the cost of producing one watch? Take the number 1 and plug it into this function up here. That's $9,009. Wow. The cost of producing 2 watches would be $9,018. Interesting that to go from 1 watch to 2 watches is only an increase of $9. That means that this is some fixed cost of running the operation and that 9 is the cost of producing an individual watch. Alright, all that being said, let's figure this thing out. We want the limit as x goes toward 1,000. We can set these equal to each other. The average cost per watch is 9,000 plus 9x divided by x. All right, that's that's what C bar represents. How should we go about evaluating this limit? Could we evaluate it by direct substitution? Well, try it. If you take 1,000 and you plug it into the numerator, you're going to get a number added to the number 9,000. 9,000 plus 9,000, 18,000. And if you take 1,000 and you plug it into the denominator, again, no problem. Could we use the strategy of dividing the numerator and denominator by the largest power of x found in the denominator? We don't want to do that here. That's a move or a technique that you use when you're sending your x value toward positive or negative infinity. Here we have the opportunity to solve by direct substitution. So I'm going to say that this is equal to 9,000 plus 9 times 1,000 divided by 1,000. And in fact, I'm just going to cancel out this multiple of 1,000 with this factor of 1,000 and this factor of 1,000 and say that my final answer is 18. So to produce 1 watch cost an average of $9,009. To produce 1,000 watches, the average cost of production, manufacturing, is only $18. The more watches you produce, the lower the average cost. I like it. I just sure hope there's a market for all 1,000 of those watches. Alright, y'all, that is 3.1. Thanks for hanging with me. I know that was a long one. There was some detailed stuff in there, but we need to continue increasing our intellectual stamina in order to grind out some problems like that. I promise you, this course is getting harder right now. It'll turn a corner and start getting easier, so just hang in there, and I will see you in the next section.